So we're going to look at some really, I don't want to say simple problems, but the kind of problems that you're going to run into a lot, not only in a calculus class, but perhaps even in a physics class, and problems that are going to involve substitution in general. So let's consider I have the integral from 1 to 4 of the secant of the square root of x over square root of x dx. Now, this is not complicated, but I cannot integrate this yet because we don't have any formulas that look like this. We don't have any formulas that when I take the derivative of that function, I get secant of a square root divided by a square root. So clearly, I'm going to need to do a substitution. Okay, that's the whole point. Generally, when you're integrating, you're going to have to substitute. And the substitution, you never want it to be taxing. This looks icky. I want to write an integral that looks easy, but the integral has to have the same numerical value. So that's why I have to also deal with the limits of integration. Now, anybody want to help me out here? What should my substitution be?
Root x.
Yeah, now here's a good question, because some folks will say, well, what if I use secant of the root x? Could I legitimately pull that off? Is that actually a possible substitution? Yes, it is. Choosing the entire function may be a possibility. The problem with me choosing the whole secant function, I'm not going to have the derivative of the secant function sitting around as part of this problem, right? I would need a secant tangent. So choosing the square root makes a lot more sense because I see this guy down here and I'm saying, yeah, that might be involved in the chain rule. So the derivative we know is just 1 over 2 root x. So I need this exactly. Well, I have almost this exactly. I need it exactly in order to pull this off. So I'm going to do this right off the bat. There. Now I have exactly my chain rule factor. I have the 1 over 2 root x. I just introduced a 2 into the denominator. So what do I put on the outside? 2 or 1/2?
1/2. Sorry, 2. 2 in this.
Got you guys. I just made the integral half as big. So my compensation is that. And that is still going to be one of the areas that we tend to get in trouble because what we did on the inside, we often do the same thing on the outside. I need to undo what I did on the inside. Okay, so that's cool. I like that. Now I need to change the variable. So right now, the range of values for x is 1 to 4. U is the square root of x. So essentially, the range of values for u will be the square root of 1 to the square root of 4. So that would just be 1 to 2. So when I rewrite this integral, this is going to become secant u du. And again, because that right there is exactly what I have. And I actually have to have the 2. I can't somehow work with that later. And my limits of integration, 1 to 2. Now, if you walked in the room right now and you saw this, that is not intimidating. Now, do I have to do a substitution? Do I have to be clever? Do I have to do something? No, we have an integration formula for this. And I noticed on the last quiz, a lot of folks were still re-deriving integration formulas that we already know. We already know the antiderivative of certain things, yet we're doing all sorts of extra work. We know the antiderivative formula for the secant. It's one of those ones that involves a logarithm. Anybody want to tackle this one? Either you have a sheet of integral sitting right next to you.
Secant u plus tangent u?
Yeah, natural log, absolute. Don't forget the absolute value. That is important. You do not have to re-derive this. You just got to write it down somewhere. I believe have I posted, God, I don't even know off the top of my head. Have I posted the calculus formulas? Actually, let me take 1 second. I'm going to check on the modules here for a moment. Let's see. Do I have the calculus formulas? Okay. I need somebody to send me an email reminder. There is actually now, you guys are now eligible for it. Before, it wouldn't have made much sense. On the syllabus for Math 151 and up, I include all the derivative and antiderivative formulas. For our class on the syllabus, I only included the algebra and trig formulas, trig identities, things like that, as things that you needed to know when you walked in the class. because we hadn't done derivatives and integrals. But now that you've done all the derivatives and all the integrals, there's actually a sheet, a page that I have that I include with every other class that I will now make available to you guys. It's a list of all the derivatives and integrals just on one piece of paper. And it's very useful. And I tell people, have that sitting right there every time you're doing your work. And the reason is really simple. At some point, you have to know all your derivatives. At some point, you have to know all your integrals. And that's not through memorization. No, that's through repetition and practice, through familiarity. When you do enough derivatives of sine x, you know the answer is cosine x. You didn't memorize it. You just did it so many times that it became automatic. But some of the more obscure ones, right, you don't do all the time, so you're not going to remember them. So I tell people, even in differential equations, have the sheet of integrals just sitting right there with you at all times. Then what happens is, okay, I glance, okay, that's the antiderivative. I glance, that's the antiderivative. Eventually you stop glancing because eventually everything's familiar. But if you don't have that, that means you're constantly stopping in the middle of work and going and looking something up. It's not very efficient. Plus, you're never really going to learn them. You want to have that available at all times. So if somebody just send me a quick email reminder right after class, I'll post it. And it'll just say calculus formulas. That's all it is. Okay, so this, okay. Now, what do we have? We have 2. So do I know the secant of 2 or the secant of 1? Do I know those? Or are those just icky answers? In other words, can we evaluate the secant of 2?
You can plug it into a calculator, see what it spits out, right?
That's not evaluating. No, evaluating would be like cosine of 0 is 1. That's evaluating.
No, we don't have anything like that.
No, and here's what's confusing. 1 and 2 represent 1 and 2 radians. You know when it's pi over 3, pi over 4, pi over 2. So in other words, you know when you're, by the way, these are angles, just lest we forget, these are actually angles. I know what to do when my angles are fractional multiples of pi, pi over 3, pi over 2, pi over 4, pi over 6. I know what to do, but these are integer valued radians. There's no conversion necessary. So I would actually write my answer as log of, now, it's still going to be absolute value, secant 2 plus tan 2 minus log absolute value secant 1 plus tan 1. And the reason I'm going to write absolute value, and then you can distribute the 2. The reason I'm going to write absolute value is I don't know if this is positive. What do you mean? Well, 2 radians is in the second quadrant. Oh, which means both of these numbers would be negative. So if I don't put the absolute value here, all hell breaks loose. I mean, dogs sleeping with cats, the whole thing. I mean, you just took the natural log of a negative number, which, by the way, is a complex number and really, really, really nasty. You couldn't even do it using a calculator. So no, I actually have to have the absolute value on this one. Now, 1 radian. How do I know the 2 radians? Well, pi is a little more than 3. Oh, so pi over 2 is a little more than 1.5. So 90 degrees is a little more than 1.5 radians. So 2 radians puts me in the second quadrant. 1 radian is still in the first quadrant. 1 radian is a little less than 60 degrees. So those absolute values would not be necessary. Now, that is the answer. But then the question always comes up and saying, well, if I'm in a physics class and now I may be referring to something, I may be referring to the amplitude of a sine wave. I may be working with an oscilloscope. That's when we have all the, the sine waves and cosine waves, and you've got to look at it and know the period and the amplitude and the frequency and all those things. And I got this as an answer. This is the answer. And I haven't the slightest idea how big this answer is. I mean, really, I have no idea what the numerical value of this is. So I'm done. That's the answer. But if I'm in a physics class, and the reason I use the physics class is the physics class, they will ask you to calculate this. See, that's the question. When I said can you evaluate? Evaluate and calculate are unrelated.
Yeah.
Putting it on here, I'm calculating it.
Yeah, because for the homework, that's what I did for some of the stuff is where I actually plugged in, okay, what's the secant of 2 to the,
By the way,
give you a decimal answer.
As a math instructor, I could care less if anybody ever used a calculator in the entire 3 semesters of calculus. Other than doing things like Newton's method, you almost never need a calculator in calculus, which always throws people because calculus sounds like calculator. No, you never need a calculator. Now, Again, most of you are gonna be taking physics. You did everything right. Let's do this on the calculator because there's some things going on here. I've got logs, I've got parentheses, I've got radians. I got to make sure I do this correctly. Okay, so when I do this, and by the way, I'm having fun because when you do this, you're probably going to get an error on your calculator. Probably. Why will I probably get an error on my calculator? Well, let's do it. Again, make sure you're in radian mode. This is just really good practice. Okay, I'm in radian mode and I'm going to go log parentheses. Now, how do you do secant? How do you do secant on your calculator?
1 over cosine.
1 over cosine. Yeah. So you go log of 1 divided by cos 2 plus tan 2. It's actually that simple. You just go 1 divided by. All right. Now I just entered everything into my calculator and I'm gonna hit equals. Isn't that mean and devious of me? I knew it was going to be an error. Can somebody tell me why my calculator gave me an error? Again?
Natural log of the trig function.
Natural log of a negative number.
Because that's a negative number. Oh, so how do I fix this? Well, since I now know that's a negative number, how can I fix that? I can't do absolute value on my calculator. Anybody want to try it? If I said in general,
Put a negative in front of the.
if x is less than 0, then the absolute value of x equals negative x. Does everybody know that this is an absolutely critical concept? If I have a negative number, then the absolute value of that thing is the opposite sign. So if I said, what's the absolute value of -2? You would all tell me it's 2, which is the negative of -2. Oh, so when I'm actually entering this in my calculator, this is the answer. But when I'm entering this in my calculator, I've got to enter it this way. I have to enter it as the negative of this quantity or my calculator. I'm showing you this on purpose because, boy, you did everything perfectly right. And after an hour of pressing buttons and getting math error every time, you're going to say, I thought I understood what was going on. You did. But you also have to realize you're inputting a negative number. That's absolute value. Your calculator is not going to do absolute value for you. You have to do absolute value for you. So let's try this again then. So this will be natural log parentheses. Okay, now I'm going to write negative 1 over cos 2 minus, where is it, tan 2. Now when I do that calculation, my calculator says, oh, it's 1.5 something. Now, subtracting this one, minus log 1, oops, try that again. Minus 1 divided by cosine 1, and plus, and ultimately everything times 2. So did somebody get a numerical answer yet? I'd like to know if we have the same thing. I tend to like to check it versus other people.
The first part I got 3.046. You said you got 1 point something?
0.59.
For this, I got about 1.59. Did anybody else? 1.5 something. Parentheses. This is what I'm saying. What did anybody get does anybody have a finished answer yet?
Yes, I got a number, but
Your final answer. What's your final answer roughly?
I deleted it to double check everything. Sorry.
I'm not saying that I did it right either. That's why I like to compare it with what you guys got.
Still working on it. I'm almost there.
By the way, do you guys understand why we're doing this problem? Because in the math sense, we were already done. But most of you are going to take a science class where the same calculation is going to come up, and you need to know how to navigate through it because this one's special. You haven't had this come up where you actually have a log of a negative and you got the absolute value. By the way, on the antiderivative formulas in general.
All right. The number I got 0.59 is my final.
Good. Yeah, I got the same thing. That gives me confidence that we both did it right. And here's the reason. I taught stats for years and years. And when I would have the class do a calculation, if any two people got the same calculation, I said, that's probably the right answer. They say, how? Because you're all independently entering the numbers. There's no possibility that two people independently can enter exactly the same wrong numbers into the calculator. So when two people got the same answer, usually multiple people did, but as soon as two people got the same answer, I knew that was probably the right answer, again, because you're all doing it independent of each other. So in the end, the answer is about 0.59, and all of you would rather just leave it like that. That was a major headache. But that is the nature of things when you're using logarithms because of the absolute value. Now, the most common error right now, if there's a common error, is that when we're doing our antiderivatives involving log, a lot of folks are not putting the absolute value in. That's actually considered a major error. That's not a minor error. If I didn't put the absolute value in here, then this is actually impossible to complete this. So you've got to have the absolute value. Now, in this case, because both of these are positive quantities, I could then put that in parentheses. That's okay. Probably safer to just leave it like that. Now, we had a problem on the quiz where it was the natural log of 2, I believe was one of the answers. And some folks left it as absolute value of 2. No, that's when you would evaluate, because the absolute value of 2 is 2, right? That's okay. But what if I'd had the log of the absolute value of -2? Well, then I would write my answer as log 2. So that's when you evaluate it when you know. There's nothing I can do here. I'm just going to leave it. But I could also do that if I had to. Now, this one here was not a complicated integration. It was a complicated calculation at the end. Now, that's not the nature of things in general in calculus. No, that's the nature of things in general in a physics class. I won't say chemistry, although logs do come up in chemistry. In fact, log is the only function that does come up in chemistry. But the ability to do this is critical. All right, let's try another one. I'm going x over 16 plus 4x to the 4th from root 2 over 2 to the 4th root of 3/4. Lovely limits. Boy, that just looks horrible. That just looks evil. Okay. Everybody got? Now, when I'm looking at this, I see a polynomial in the denominator. When you see a polynomial in the denominator and you see something in the numerator, what are you hoping for? Anybody? Because
One power or less.
Yeah, because if the numerator is 1 power less, then there's a very good chance that the numerator is what? Versus the denominator.
The derivative.
Perfect answer. If the numerator is of degree 1 less than the denominator, then there's a really good chance. In fact, that's exactly what we'd be going for. So if my numerator is an x cubed, then clearly my denominator is u, and then I have a multiple of du on top. Life is good. Life is easy. That's not the case, is it? Okay, so you're always looking for derivative on top of function. You're always looking for that, and that's u to the n du is the most common antiderivative you'll ever run into. But the second most common is the 1 over u du. That's the second most common. And this isn't quite that, right? The degree difference. So therefore, the next thing I'm going to look for, when I'm looking at the denominator, now what do I see? A sum of what? Squares. That's, by the way, that's not the first thing I'm looking for. That's the second thing. And just so you know, if this is an exam, I'm going to ask, I do this, I'm vicious and devious like this. I'm going to ask these questions one after another, just so you know. I always do this because they look like the same question, don't they? Degree difference of 1. Oh, this is just going to be a 1 over u du. This one, I'm out the door really quickly. This is not. So therefore, the next thing that I do is I see the denominator as 4 squared plus what?
2x squared.
Now, if that's my u, can this potentially be the du on top? Yeah. Now the degree difference is 1. Okay, that's when you know to do this. And so, by the way, I have a 4th power on the bottom. I have a 1st power on the top. What if I had a 6th power on the bottom? No, it won't work. What if I have a 5th power on the top? No, it won't work. It has to be exactly the right thing. Either a degree difference of 1, or if I see the bottom as a perfect square, then the degree difference is 1. If either one of those weren't the case, then I can't do a substitution. It doesn't mean it can't be done. It can't be done using the substitution that we just learned. And then basically it becomes a Calc 2 problem at that point. So I'm going to let u equal 2x squared. then the du is 4x dx, and that's one of the easier things to make sure. So now I have exactly my du that I need, 1/4 on the outside. I'm introducing the 4, which is why I introduced the 1/4. If I had already had a coefficient on here, then I would have factored out the coefficient. But I don't have a coefficient, so I'm introducing it. Now the change of limits. Well, my original limits are pretty scary. But my change of limits, maybe that won't be so bad. So √2/2 to 4th root of 3/4. So yeah, who could be this evil besides me? I mean, all right. Well, when I insert √2/2 to where the x squared is, I don't want to do that in my head. Let's write it down. I'm going to insert that into there. So I have 2 times √2/2 squared. What does that equal?
1.
1. Oh, maybe that wasn't so bad. Do you all agree? Maybe that's not the worst thing I've ever seen. Now let's do the same thing with the other limit. Let's take this and substitute it in there. So now I have the 4th root of 3/4, but I'm squaring it. What happens when I square a 4th root? In general, if you square a 4th root, what does it become?
Doesn't that take 2 off of the
A
power?
square root?
It becomes a square root. And by the way, here's an easy way to think of that one. I'm looking at that. That's not intuitively obvious. So let me write it a different way. I want to square the 4th root. Isn't this the same as saying x to the 1/4? Isn't that the same thing?
Yeah.
Oh, and I multiply exponents. That's the proof. If I square a 4th root, I get back a square root. You don't, that's not memorizing. That's not some weird property that you're all supposed to know. No, you just squared a 4th root, which means you multiplied your 1/4 power by 2 and you got a 1/2 power. That's it. That's where it came from. So when I square this, this is going to become the square root of 3/4. Well, isn't that the square root of 3 over the square root of 4? And can I just go like that? Is that valid what I did?
Yes.
So therefore, that's just √3. So those original limits, absolutely terrifying. My new limits, I don't know. Maybe they're not bad at all. Maybe that will make it easy. Well, let's see. So this now will become 1/4. The integral from 1 to √3. There's my du, so it's now 1 over, don't write 16, write 4 squared. Why? Because if I write 16, then mentally I'm going to work 16 into my answer. The answer doesn't have a 16 in it. The answer has a 4 in it because the antiderivative. What does this look like?
Inverse tan?
Inverse tan. Perfect. Inverse tan. Now I have a 1/4. I have inverse tan 1/4 u. This guy shows up again or not?
Yeah, you need the inverse A.
Shows up right here. I'm gonna put a little arrow. That 1/4 is right here. This 1/4 comes from the antiderivative formula, right? We all know a squared plus u squared du. The answer is 1 over a inverse tan, like you said. So that one, that 4 shows up here as a 1/4. I already had a 1/4. The common mistake obviously would be to forget that one. And that one is critical. And I'm doing this from 1 to √3. Okay, is √3 a good number? I don't know. Maybe, maybe not. So right now, what do I got? I've got 1/16. I'll write like this. Inverse tan of what?
√3 over 4.
√3 over 4 minus inverse tan of
1/4.
1/4. We know inverse tan of 1. That's pi/4. We know inverse tan of √3. That's pi/3. We know inverse tan of √3/3. That's pi/6. The only ratios that are common for tangent, by the way, are 1, √3, and √3/3. With sines and cosines, the common ratios are, we know, 1/2, √2/2, and √3/2. So with each particular trig function, the common ratios are the ratios we get when we insert common angles. Common angles, again, would be 30, 45, 60. Okay. Are these common ratios for a tangent? In other words, when I take the tangent of an angle, do I generally see 1/4? I just said we see 1, we see √3, we see √3/3. When you take the tangent of an angle, do you see 1/4 ever? Can you think of an angle where you'd see 1/4?
No.
No, I'd have to use my calculator and do it, you know. So when I do, for example, if I do inverse tan 1, when I do inverse tan 1, it's going to give me that's the decimal of pi/4. Okay, so let me go back. By the way, one of the things I always suggest when you're doing inverse trig functions is actually set your calculator in degree mode. And there's a simple reason. When I do inverse tan 1, it's going to say 45 degrees. Aha, and now I know. Okay, I'm going to give pi/4 as an answer, but my calculator said 45 degrees. Okay, so now I'm going to do inverse tan of 1/4. I have it in degree mode so I can recognize. And of course, that's my answer. 14 point something degrees. Oh, that's not a common angle. 30, 45, 60. Those are common angles. I got some goofy decimal. Well, all that means is I can't evaluate this. So I'm just going to leave it alone. That's my answer. Now, if I do need a decimal approximation, that's easy enough. But now, like the last problem when we had absolute values and we had to work around them, if I'm going to do the calculation on this one, and again, I'm not into calculations in general, but today's class is actually all about using our calculator, really. Let's do a calculation of this. Now, I have to be in radian mode. You cannot do a degree calculation. It won't be the same answer. The reason it has to be in radian mode is radian is actually a measurement. For example, arc length is measured using radians. Area is measured using radians. Pi r squared. You don't say 180 degrees r squared. You say pi r squared. And that pi has to do with pi radians. So let's do this. So I'm going to have inverse tan. And everyone try this because I like to see we all get the same answer. √3/4 minus inverse tan 1/4. And then all of this over 16. So when you get an answer, tell me.
0.0102.
Yeah, a little bit bigger than 0.01. That's really small. Okay, but that's the answer. Okay, so this is the answer. This is all I want to see. This is all I ever want to see. This is a math class, but you're taking your math skills to other classes. So I'd like to know that you actually can execute the calculator. Again, that's the answer. I could care less what the decimal is. I have a calculator. I can always calculate the decimal, but I'll tell you something you cannot do. It's an absolute impossibility. Technology will never be invented ever. I've already looked into the future. Technology will never be invented that can take this and give you this. That's not possible. Can anybody tell me why is it not possible for me to take that answer and work backwards?
There's an infinite possible set of equations.
This is rounded to the number of decimals on my screen, which means there's an infinite number of things that would have produced this answer. So when people write silly things like 1/3 and they write equals 0.3, there are an infinite number of simple things that would round to 0.3 if I just did one decimal place. Heck, 3/11ths would round to 0.3 if I'm only going to do one decimal place. Okay, so when we're rounding, you can never work backwards from a rounded off answer and say where it came from. That's not possible because there's an infinite number of things that would have rounded to that same thing. So that's the answer. That's the decimal. Be aware of how to calculate the decimal because that requires a calculator. But in the math class, we want the answer because anybody can convert an answer to a decimal. Nobody can convert the approximation back to the answer. You can convert an exact value. So in other words, if I said my answer is exactly 0.5, yes, That's a half.
Professor.
Yeah.
I'm sorry to interrupt. Real quick before you erase all that, can you just what was the answer again? It was 0 point. I'm sorry, yeah, 0
I
point.
believe we said, I erased, I believe it was, I
Okay.
don't remember what follows, something like that.
Yeah, okay, yeah. I just want to make sure. 102, okay.
Yeah. I think
Thanks,
it was, Bill says 02. I'm only saying that so that you know that you hit the right buttons eventually.
Yeah, I didn't.
The actual value is not really.
Gonna have to try again.
And by the way, don't feel bad if you're not getting the answer right on the first try. I don't always get it right on the first try. What I do when I'm on my own, and again, I taught statistics for years and people never understood this concept, but I have this powerful calculator. If I'm doing a calculation, I always do it twice. And if I got the same answer, hopefully not 10 times skill, but I always do it twice. And if I got the same answer, I'm good. And we all know what happens when you do it the second time, you get a different answer. So then you do it a third time, praying that you get one of your first two answers. The reason, I don't care what technology you're using. I don't care if you have a supercomputer. Why can you get different answers? Because you entered the numbers. And when you're entering the numbers, you might make a mistake entering the numbers. So when I'm doing a calculation, I can easily make a mistake in entry. It has nothing to do with the power of my calculator. It's the fatness of my fingers. It's like when I'm texting people, I'm looking going, that's not a word. That's not what I wrote. My fat thumbs are hitting the wrong keys. Same thing. It's there's no such thing, by the way. I always laugh. People say, oh, it's a calculator error. It's a computer error. No, it's human error. The calculator did exactly what I told it to do. I just gave it the wrong instruction. I hit the wrong button. That's not a calculator error. That's my error. That's why I always do it twice if I'm interested in numerical calculation. Now, we're going to do one more example, and then we're going to go to an application that actually doesn't require any calculus, just a calculator, right? So the last one I want to do, and this is not complicated, but I wanted to get in some different functions. Integral from 2 to 3 of the hyperbolic cosine of x cubed times 4x squared dx. Now this one here is less taxing than the others, but we haven't done a lot with hyperbolics recently. Okay, now we know the antiderivative of the hyperbolic cosine. That's easy, but I got hyperbolic cosine of stuff. Okay, well, that's not an x, so that's going to be my u. All right, Nate, I can always tell when you're not muted. Now, I don't have exactly that. And in fact, this is not a convenient one. You know, if that were a 6, oh, I just factor out a 2. If that were a 1, then I just didn't insert a 3. I put something not quite right there. So you guys remember the trick? Well, not really a trick, but how do I walk me through it?
Well, can't
Factor
you?
out the whole number.
Oh, I was gonna just say, can't you just like times by 3/4? Since but this is just jumping that we know that the 4 on the bottom and the 4 on front would cancel out though.
Throw a 3 in there and then put one on the outside also, right?
Where's it on the outside though?
On the denominator.
How do I know? Because 4 over 3 times 3 is 4. That's the ultimate proof.
Well, what's the difference?
Okay, stop.
Sorry, what's the difference from that and adding?
Hey, stop talking for a minute, okay? I've already explained it twice, and now I'm about to do it for the third time, and you're going to interrupt me again, so you're going to make me do it a fourth, a fifth, a sixth time. I'm not introducing a 4. I'm pulling it out of the problem. I'm factoring it. That's why 4 stays in the numerator. Now there's a 1 here. I'm introducing a 3, so I have to introduce its reciprocal. That's it. There is no other step ever. There's no other step that exists. That's it. When you're factoring out the number, it's on top. When you're introducing, you must introduce its reciprocal. There's no other possible steps that can be done ever. That's it. Now, if I can see, I'm just going to multiply by 3/4. And then when you put 3/4 on the outside and you get wonked over the head for, messing up the problem, you go, but I did it in my head and it was 3/4. No, it was 4/3. There is actually no 3/4 in the problem. There's a 4/3. So that's why I don't like it when people try to do it in their head and then get the wrong number on the outside. No, this is too simple to get that right. But still, the reciprocal of what it's supposed to be is the most common error because we do things in our head and we've got the wrong numbers. I want you to be right because that's just not hard. But that, I gotta get that right. Now, as x goes from 2 to 3, I'm sorry, x goes from 2 to 3, the value of u will range from what to what?
Is it 8 and 27?
8 to 27. Those values they're not important. They're just the new values I'm going to get. So we don't want to read importance into them. The numerical value that this one's going to produce will be the same numerical value my new one will produce as long as I use these values. You say, oh, 8 is special. Well, no, it's just 2 cubed and 3 cubed. So 4/3 hyperbolic cosine of u from 8 to 27. Now, when I walk in the room and I see this problem, there's nothing about this that's scary. So my answer is 4/3 times, is it positive or negative?
Positive sign, hyperbolic sign.
Yeah, the hyperbolics for sine and cosine, both antiderivatives and both derivatives are positive. And there's one of the things that we sometimes get mixed up, because with regular sine and cosine, I know there's a negative in there somewhere, but with hyperbolics, there's no negative in there. I like that. I'm less likely to mess that one up. So I have 4/3 times the hyperbolic sine of 27 minus the hyperbolic sine of 8. That's it. I do not need to do anything else. Would it be legal to change it to the exponential version, the e to the x, e to the negative x and all that? Would that be legal? Sure. Would it be useful or efficient or even make my life easier? No. No. Writing this as 1/2 e to the 27th minus e to the negative 27. These are the same thing. Where's the advantage created by writing that down? I still don't know what that value is as a decimal, so I just leave it like this. Now, if I really needed a decimal value, hold on. Then I just simply hit hyperbolic sine on my calculator. 27. This is going to be astronomically large, by the way. Wow. How come it's so big? Because you got this in the problem. See, if I really needed to calculate, this isn't useful to me. It's just too big. So I'm going to leave it like this, or I'm going to give a decimal answer. One or the other. For our purposes, we leave it like this. Okay. So this is our, well, not our review. This is our extension of integration using substitution. And you notice that the format doesn't change. The integrands are going to change, but how I do it, I select my u, I find the du, I make sure I have exactly du in the integral before I continue. I change my limits, I integrate, boom. Pretty fast at that point. Once I change my limits, then I have the antiderivative evaluated, I'm done. Once you change your limits, every problem is exactly 2 steps. There are no additional steps. I integrate, I evaluate. Now we're going to do something today. It's kind of a what if. I've got a problem here where I'm asked to find, let's say, the area under the curve. Okay, I want to find the area under the curve. So I already know, let's say this is y equals f of x. I know that the answer is the integral from a to b of f of x dx. My what if is, what if I don't know the antiderivative of that? What if this cannot be integrated? What do you mean it can't be integrated? There's an infinite number of integrals that cannot be integrated, even though they look like ones that can. I'm going to give you a simple example, real simple. I've got the integral of e to the x. I've got the integral of e to the x squared. Easy. Can't be done. In fact, any exponent I put here that isn't a simple multiple of x. What if I said e to the tangent of x, e to the cosine of x, e to the anything? Can't be done. Why? Because there's no chain rule factor. Oh, will I learn how to do it next semester? Nope. The antiderivative doesn't exist. Easy doesn't exist. For every function that you know the antiderivative of, if you just tweak it slightly, there's a high probability the tweakage will not have an antiderivative. Now, there's other things we learn next semester to deal with that thing, but I can't integrate it. So let's just pretend for a moment that we don't know the antiderivative of that. Maybe it's something we're going to learn in the future, but right now we don't know the antiderivative, but I still need a value. I'm doing something and I need a value. Even if I can't calculate it directly, I want to come up with a reasonable estimation. Now that's a tricky one because reasonable is kind of loose. When we did the tangent lines leaving the curve and we used the value on the tangent line to estimate the value on the curve, remember we did that many weeks ago. As long as I didn't move too far, the value on the tangent line was really close to the value on the curve because we cheated. We used our calculator and we compared them and said, oh, I'm really good estimation. But realistically, when you're doing an estimation, you can't find the exact answer. Because if you knew the exact answer, why would you be doing an estimation? If I know the answer is pi, why would I be doing an estimation of pi? I just know, I'll just say it's pi. So let's pretend we can't do this. So what if I did the following? I want to divide this, okay, evenly this time into, so I have n partitions. Right, so like always, that'd be x0, x1, x2, you know, and then that would be xn. But I don't want to make rectangles this time, not this time. I want to do something else. I want to just connect the endpoints. Sorry, this is not a very good picture, but I'm just going to connect the endpoints. Now, if I said, let's find the area of each of these shapes, obviously that would be pretty good. That'd be pretty close to the exact value. Now, it would be impossible for it to be the exact value, but it ought to be really close. But those aren't rectangles. I mean, want to tell me what those shapes are?
Trapezoids.
Trapezoids. Ooh.
I went ahead in the book.
Oh, well, actually, it also says so in the syllabus. Those are trapezoids. Those aren't rectangles. I mean, I'm going at an angle. And
Well, you said sorry for interrupting, but you said yourself that it's still not going to be perfect. It's just a little bit closer. So why should, if it's still not accurate, why should we prefer this over the rectangles?
You shouldn't.
Yeah. So I mean, so we could look at a problem and do it either with the rectangles or this way.
This is just infinitely easier.
Okay.
This will take you 1/10,000th of the amount of work.
Oh, if it's easier, then by all means, please go ahead.
No, it's not even comparable. The difficulty level drops significantly. and all you need to do is this cheap calculator. So I have a trapezoid. How do you find the area of a trapezoid again? Do you guys remember? It's actually pretty simple. It's the average of the bases times the height. The area of a trapezoid is the average of the bases. So quite literally, and I teach this in remedial algebra, it's just good to know. If I took the average of the bases, then my orange rectangle will have the same area as my trapezoid because I just took the midpoint of these sides. Oh, okay. So this length is the average of B1 and B2. Okay, great. So how do I know I have trapezoids? Because the definition of a trapezoid, it's a quadrilateral with one pair of parallel sides. A parallelogram, both pairs are parallel. Trapezoid, only one of them is parallel. Okay, so with that, these are just trapezoids sitting on their sides. So here's the only assumption we're going to make in this problem. We're going to do it so that all of our delta x's are equal. Okay, now Riemann sum, they're not equal, but all of these delta x's will be equal. So if I said I have n partitions, and I'm going from A to B, we've done this before. I have n partitions and I'm going from A to B, then exactly how big is each delta x?
B minus A over N.
Beautiful. And by the way, A, B, and N are known before you start the problem. So that already is a simple fraction. It might be a half, a third, a fourth. It's going to be a simple fraction every time. So if I went from 2 to 6, and I've got, 16 trapezoids. Well, 2 to 6 is a width of 4, so each one would be 4/16 or 1/4. I mean, that's it. It's actually pretty simple. So what I'm going to do is using that, in other words, that's my height. If I put these on their side, oh, delta x is the height of my trapezoid, isn't it? Then what are my two bases? That would be the two lengths. Okay, so let's do this. Let's call this, make it simple, let's call this A1, A2, A3, dot, 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 all the way up to AN. Okay, what is the first? Well, it's the average of the bases, so it's 1/2. But what are the bases? Well, that would be one of my bases. That would be f of x0. What's the second base? F of x1. That's the average of my bases, because again, you're looking at it sideways, times my height, which would actually be delta x. Okay, what's A2? Well, that'd be 1/2 f of x1 plus f of x2 times delta x. I'm gonna go dot, dot, dot. All the way to my last one, which would be 1/2 f of x, how about n minus 1 plus f xn. Xn would be the last one, xn minus 1 would be the one right before it. Oops, delta x. Okay, so hopefully everybody see this is pretty simple. Again, this is the equation or the formula for the area of a trapezoid. I have exactly n trapezoids. Now I can say that my area will be estimated by the sum. Whoops, I have n, sorry, I'll use I equal 1n. So I'm going to add this one plus this one plus this one plus this all the way down. And that's my answer. We haven't done any calculus, have we? There's no calculus whatsoever. I just do simple calculations. Now, this ought to produce a formula that isn't terrible. I'm going to erase this. I'm going to produce a formula that may or may not be terrible. But when I add all these up, when I add all these together, you do notice something. First of all, I can factor out the 1/2 and the delta x. So the sum of the AIs, let's write it as 1/2. Let me go like that. So now what goes inside? Well, the guts would be f of x0 plus f of x1 plus f of x1 plus f of x2 plus, and then f of x2 plus f of x3, right? And then my very last one will be f of xn minus 1 plus f of xn. Okay, this is what's going to go inside. So do you notice anything? The right, the base, I have two bases, call it, base 1 and base 2. The second base in the first trapezoid becomes the first base in the next one. The second base in this one becomes the first base in the next one. So every base is going to be repeated, isn't it? Or is every base going to be repeated? Well, almost all the bases are repeated. In other words, that one's only going to happen once, isn't it? 2, 2, 2. Is there any other one that's only going to happen once?
Last one.
Last one.
Yeah,
last
last one.
Because this was the farthest left and everything else got included. This was the second to last, so it got included. So what this gives us is a really, really simple formula. So we can now say, here's how we write it. The integral from a to b of f of x dx can be estimated by 1/2 f of x0 plus, and I'm going to write it the way that you'll generally see it in the textbook. 2 f of x1 plus dot, 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 plus 2 f of xn minus 1. The implication here is every single one of these has 2 plus f of xn all times delta x, because that's how we set it up. Everything gets a 2 except the first and the last. Now, we're going to walk through a problem from beginning to end, and you're going to see how it works. Now, this is an estimation. So the numerical value that I get on my calculator. Now, this is one I actually do want to do the calculations. The reason is I'm saying I have an integral. It has an answer, whatever the answer is. I'm going to do an estimation. I don't want to leave my answer as, square root of 2 plus pi minus 3/2. That's my final answer. Well, no, I actually want a decimal value because the decimal value is the estimation of the integration. So we'll do it with the actual numbers, and then we'll just use our calculator. So let's do a problem. My pens are running out of ink. Let's do, I have the integral from 0 to 3 of, let's say, 1 over 16 minus x squared. Okay. Now, we don't have an antiderivative formula for this. Now, I kind of cheated. Next semester, we're going to learn a technique that will allow us to do this problem. Okay, next semester. But for all practical purposes right now, we have no idea how to do this problem. Okay, but I'm going to tell you right now, the answer to this is the actual answer. We don't know how to find that answer. So for as far as we're concerned, we cannot do this one. And the reason I'm giving you the actual answer now is so at the end of the problem, when we're finished, we can actually compare our estimation to the actual answer just to see how close we really came. I will do this on occasion. The vast majority of the problems that when we're doing this, you can't find the exact answer. The reason you're doing the problem is because it can't be integrated in the first place. But sometimes I like to borrow problems that you're going to learn how to integrate next semester and do them now so that I can actually give you the answer. On the quiz, I did that. On the quiz, I gave you the actual answer in parentheses. By the way, that won't help you do the problem, not at all. But it means at the end of the problem, when you get a decimal value, you can compare it to what it's supposed to be. And if you're close, then you know you did it right. But also you can see, wow, my estimation was ridiculously accurate. So here's what we're going to do. Oh, by the way, we have a really clever name for this process. Now remember, math people, we're the people that brought you, when you have a point and you have a slope, we use the point slope formula, right? That's our formulas sound like what we're doing. So the rule for taking derivatives of products is called the product rule. We couldn't think of anything more clever than that. So we're going to do an estimation of an integration using trapezoids. So the rule that we're going to use is, we call this the trapezoid rule. Yeah. Again, it would be cool if we kind of come up with some 007 method, just some cool name for it. No, it's called the trapezoid rule. What people don't like in math is when a theorem or a formula is named after a person. We don't like that because then we don't know what it means. But almost every theorem and formula and everything in math is, it's the formula that does this is called the formula that does this formula. And it makes it easier to remember. This is called trapezoid rule. So we're going to use trapezoid rule to do this problem. The only thing I have to tell you, there's only one thing. I have to tell you the value of n that you're going to use. You do not choose n. And the nice thing about this is you never choose large values of n, ever. I mean, you're never going to choose a value of n, maybe even as big as 8. Heck, most of the homework problems in the textbook will either use 4 or 6. I can get a ridiculously accurate estimation with very, very few trapezoids. That's the whole point. So let's do this with an n of 6. That means I have to do 6 partitions. With that said, then what is the value of delta x in this problem?
1 over 2.
Yeah, so how do I find that?
B minus a over n, which was 6.
Perfect. And by the way, I can't afford to mess that up. I got to get that right because that will mess everything else. Now, I'm going to walk you through the order of things. Okay. This is not an area for creativity. Technically, this is an algorithm, which means that all human beings doing this problem should do exactly the same things at the same time in the same order. And then everybody gets exactly the same answer. So I need now to find x0, x1, x2, x3, x4, x5, x6. Do I keep going? No. And it was 6. So that's my last one. Okay. Those aren't given. I have to state them. Now, what's x0? 0. What's x6? What's that one? Anybody?
Is the 20? Oh, sorry, 1/20th.
1/5. Oh, it's evaluated at 3?
What's x6?
X is 6 is 6 squared, which is 32.
No, no, no,
No?
no. Keep kind of. What's x6?
Is it 1/7?
What's x6? What's x6?
3.
3. Oh my God, guys, you're killing me here. These are the x coordinates. They're not.
Yeah, that
valid
makes sense.
Coordinates. X0 is your first one. Xn is your last one. That's what we've been doing for a while. Now, why am I writing that down? So I can fill in all the other ones correctly. If you have any errors anywhere, any answer you get is going to be meaningless because it won't be similar to the problem that you're attacking. X0 is my starting point. X6 is my ending point, and I'm going to count by halves. Okay. Now, if I'm counting by halves, please fill these in for me. Tell me what all of those are. There's no ambiguity there.
177,345.
So what would X1 be?
1/2.
Half.
Half. What's X2?
1,
Keep going.
1.5, 2, 2.5, then 3.
Well, considering that you would never enter a mixed number into a mathematical
3/2.
equation,
Oh,
yeah, you
then
probably want to leave them as improper.
5.
Yeah, I've never done a mathematical operation in my life where I entered a mixed number. And if you did, you almost certainly got the wrong answer. Yeah. So now, okay, if I count by halves, I get to here. Beautiful. Why is that important? Because now I need to do the f of those. Now, what is f of x? F of x is my integrand. That's not something you have to figure out or interpret. Remember, you're doing the integral of f of x dx. So now I need, the next thing is, what's f of 0? What's f of a half? That's why you have to state these, otherwise you wouldn't know what to calculate. I state all my x's so I know exactly what it is I'm going to calculate. Now, this is the meat of the problem. We haven't really done anything yet, have we? We figured out what our delta x was, and then we just wrote all our x's, x0 to x6. If that was a different number, then this would be a different number. But first and last wouldn't have changed, just how I got there. Right? The amount I added would have been different. So what am I doing with each of these? I'm inserting them into the integrand. So what is f of 0? Let's start with the easy ones. Let's do the integer ones. F of 0 would be what?
1/16.
1/16.
16th. Beautiful. What's f of 1? F of 1 would be
1/4.
f of 1.
Oh wait, I'm sorry. Never mind.
It's not 1/15.
150. Well, no one said it.
Yeah.
What's f of 2?
Oh.
What's f of 2?
1/12.
1/12. Some of you guys are thinking way too hard. And f of 3?
1/13.
1/7.
1/7. Okay. Now I got to do the halves. So let me do the half now. So f of a half, that'd be 1/16 minus the square of a half. Yeah. Well, okay, what would that be? That'd be 1 minus 16/4. I really don't want a fraction in my denominator. That kind of makes it icky. There's a couple things I can do. I can simplify the denominator and then multiply by reciprocals, or I can be lazy. See, I'm lazier than you guys. I would go like that. So what's that? 4/64 minus 1. Less work. Again, I don't want to enter a fraction within my fraction, and then I'm going to have to enter it into my calculator later. I'm going to mess it up. If I make the statement of this complicated, you're gonna have an entry error in your calculator later. So when I do this, that's f of a half. Simplify it as a simple fraction. Just make your life easier. Now, what about f of 3 halves? Let's do the same thing. F of 3 halves is 1 over 16 minus the square of 3 halves, which would be 1 over 16 minus 9/4. So if I just simply go 4 over 4, that's going to be 64 minus 9 on the bottom. That'd be 4 over 55. And I'm running out of room here. 4 over 55. Okay. I have to do these calculations. And by the way, would there be anything wrong with putting decimals down? Yeah, these aren't terminating decimals. You don't round off, you do not calculate and round off these. You calculate and round off your final answer. But if you calculate and round off your input as an absolute mathematical money back guarantee, no matter what you report, your last decimal place or your last decimal places will always be incorrect because you were calculating the wrong values. You can't round a number off and then re-enter it and expect that you're going to get the same value. No, you round off the results, not the intermediate. Newton's method is the only time you round off the steps because you're going for convergence. We're not trying to converge to a decimal. We're just trying to give a decimal. So I want these to be the simplest they can be. Now, if your values were terminating decimals, sure, but 1/7 is not a terminating decimal. Why would I want to put a decimal down? I'm just going to enter that on my calculator. Too easy to get it right because I have a calculator. So this would be 16 minus 25/4. And by the way, if you have a fraction key on your calculator, this is already doing this for you. You can be really lazy. So that's going to be 4 over 64 minus 25. Beautiful. Now, the next thing I write down is essentially going to be my final answer. And from the standpoint of, I just have to use my calculator. So I did not leave myself a lot of room here. So now we can say 0 to 3 of 1 over 16 minus x squared dx is going to be estimated by 1/2 of that number plus 2 times that number plus, sorry, I'm gonna have to write it in this format, 2 times that number plus 2 times that number plus 2 times that one plus 2 times, where are we now? 4 over 39. And then finally 1 times that number. And the whole thing is being multiplied by delta x. Now, here's where people get in a little bit of trouble. Both of these are a half. This half is from the formula. There's always a 1/2 right here. Is there always a 1/2 right here? What do you think?
No, that's the delta x, isn't
That's
it?
the delta x. If I had given you a different n, you would have gotten a different value, but you still have the half here. That's the formula. That clearly that can be tricky. And what's worse is most textbooks, when they do the problems, they love using delta x as a half just because it's easier. But the next problem might be delta x as a third. The next one might be delta x as 3/4. Delta x is going to be something simple. But that number you calculated, that number is part of the formula. Now, clearly, this is a rational number. That's absolutely correct. But I do not need you to simplify that as a fraction. Whatever the numerical value of this is, that value serves as my estimation. So now I'm going to use my calculator and I'm going to calculate this. Okay, so use your parentheses wisely, or you can be really, really lazy. If you really don't like doing all the parentheses, what I would do, what I do is I calculate the guts. Then I do these last. Then I don't have to use any parentheses. So yeah, I'm lazy and it actually I get there a lot faster. So let's all do this now. So everyone do the calculation. Let's see if we agree. Write down what I got here. So when you get a number, just let me know. Because again, this is one of these areas I really like us all to get the same thing.
I got one.
What do you got?
0.246.
Good, good. So you got the right. That means that I didn't hit a wrong button somewhere. Now, again, there's nothing difficult about this, but the fact that I have to enter so many numbers, it is very wise to always do the calculation twice. All right, so here's what I'd like to do. I'm going to put down a few decimals. And by the way, when people say, well, how many decimals should we report? The answer is yes. It doesn't matter. You're doing an estimation. So if you put down 1 decimal or 10 decimal places, it's an estimation. You're not saying that any of your decimals are necessarily correct. Your first decimal might be correct. It might not be. Your second one might be, it might not be. You don't know. So now let's actually answer the question. Sorry, this is hard to read. So here's the answer to the question. By the way, I put a bunch of decimals just so I'd have something to compare to. You can put as many as you want. You can put as few as you want. Just make sure whatever you're writing on you rounded correctly on your calculator. Now, that's my answer, okay? Oh, I probably erased too much stuff here. That's my answer. Now, I told you the actual answer was log 7/8. Now, generally speaking, you couldn't know this. But again, because I'm introducing this, I wanted to give you something to compare it to. So if I calculate this, this is approximately 0.24324 if I went 5 places. Fairly close. What do you think? They don't differ until the 3rd decimal place. So they're only off by
2.5 thousandths.
They're only off by yeah, you'd say, you know what? I did 6 trapezoids. And I'm only off by a couple of thousandths. I don't know. I think it's pretty good. You see, what if I wanted more accuracy?
More trapezoids?
Trapezoids. You say, but boy, that's a lot of work by hand. But in real life, you write a computer program. Okay. Everybody here who's ever had programming, day 1, a do loop. Right, we've talked about that from I equal 1 to 1,000 do. You write the algorithm and it calculates faster than you just did on the calculator. And
Right.
More trapezoids would mean less over under, less deviation. Now, in reality, remember, in reality, we don't know the answer to this in reality. So we go with this. How many decimals is not even important. I know this is an estimation of my answer, but I did this just to show you just how really good this estimation really was. So trapezoid is a really good technique. It's not the only one. I'm going to show you another one. And the reason trapezoid isn't the only one, I'm going to erase this, but I'm going to ask you guys what the numbers are because I'm not going to recalculate them. I'm going to state something, okay? This was our first answer. I'm going to leave this up here for a moment. All right. Actually, I'll write it up here. Trapezoid rule, we got 0.24573. We're going to do a second technique and I want to compare the answers. So let me throw a what if at you. I have a curve that's changing wildly. And I want to do, a a few trapezoids, however. I have a curve that is changing wildly. So it has lots of concavity changes, maybe direction changes. Even if I did a lot of trapezoids, do you think my trapezoids are going to give me a really, really good estimation in that picture? Anybody?
No, they're not equal.
Well, no, it's never going to be equal. It's impossible. There's no problem that exists where you would get equality because your trapezoids will never equal the area of the curve. but in the last example, it's really close. I'm just saying, I have a curve that changes wildly. Even if I do more trapezoids, the amount that I'm cutting off, the trapezoids would not give me a very accurate area. Do you agree with that? I'm trying to make it extreme and really obvious. Trapezoid rule is only really, really good if your curve is slow moving. You see, if my curve moves really slowly, then the over-unders, if I like to call them, the curve, it's slowly moving curve. Then any set of trapezoids that I do in this case, I don't have a lot of over-under. If my curve's moving slowly. Now, the problem is, without actually looking at the graph, you don't know if your curve's moving slowly or it's changing wildly. So there's a second technique that I'm not going to derive from scratch. The derivation's in the textbook. It's actually really long and it's all geometry. But what if I have a curve that's changing rapidly? Well, it turns out there's another shape I might want to use. What if I used parabolas? Now just think about that logically. If I have a curve that's changing wildly, what if I used parabolas rather than trapezoids? I mean, that's kind of an odd choice. Whoever thought of this. But if I use parabolas, it turns out I will get a very, very accurate estimation. And the formula is really, really similar. Now, the derivation is not complicated. It's basically you're taking a quadratic, you're integrating it, and when you integrate the quadratic, you get a third in front of the x squared term. And so this one ends up having a 1/3 in it rather than a 1/2. And so the second formula looks like this, that the a to b of f of x dx 1/3, and it starts the same way, but then it's 4, 2, 4, with this alternating patterns of 4, 2, 4, 2, then 4, and then just one of the last one. Oops, sorry, I'm not going to fit this on very well. I'm still not going to fit. Shoot, sorry. Times delta x. Okay. There's an alternating pattern of 4s and 2s. In this one particularly, n has to be even. N has to be even, or I don't. What you're essentially doing when you're doing your parabolas is you're splitting it up into thirds, and when you add them, you're always adding. It has to be an even number. Okay. The derivation in your textbook will show you that. So n has to be even, so the 4 goes in front of all of the odds, and everything else gets 2s except for the first and last. This formula looks almost identical to the trapezoid rule. It's slightly different, and most of the time actually gives you a slightly better estimation. We're going to do it in a moment. Now, this formula was named after a very, very famous French mathematician. I believe the pronunciation of his name was Omer Simpson, I believe was how his name was pronounced. And so this one here is actually called Simpson's rule, named after the famous Omer Simpson, whose head was shaped like a parabola. So I don't know. I think that's where it came from. You guys might want to do a little research on the internet for, Omer. I'm pretty sure that's how it's pronounced, but I could be wrong. But this is called Simpson's rule. And people will always say, what's a Simpson? This one is basically, could have been called the parabola rule, but the derivation was a little more complicated. Trapezoids was very, very simple. Okay, so let's do the last problem. Let's do this problem using these values. Okay, so you're going to help me out here because I've erased everything. So we're going to have 1/3. Now, what was our f of x 0? I know that was 1/16, was it?
Yeah, it's 1/16.
Okay. 4 times, then what was our what was that one?
4/63.
4/63. And then
1/15.
And then 4.
4/55.
55. And then 2 You know,
1/12.
can I get one more?
4/39.
4/39, and then there was one more plus
1/7.
1/7, and that's the last one. Those guys don't get coefficients. And again, our delta x was still a half. Now, what I'd like everyone to do, and by the way, in terms of which one is easier, which one's harder, exactly the same level of difficulty, because in both cases, you had to find these values. And the only difference in the calculation are the coefficients. In the trapezoid rule, it was 1, 1, and then all twos. In the Simpsons rule, it's 1, 1, and then alternating 4, 2, 4, 2, 4, 2. Okay. That's still delta x at the end. 1/2 in the trapezoid rule, 1/3 in the Simpsons rule. So let's all calculate this and see what we get. All right, let me know when you got a number. I got one. This is where having a cheap calculator is very beneficial.
I got an answer.
Is it close to the first one?
Absolutely not. I must have messed up.
So here's the quick proof. It should be close to the first one. It can't be the same, but it should be relatively close. Does anybody else have a number? I got a number. And my number is close to the first one, so I trust it.
Could you step to your left just for a second? I got to start over.
You guys got these written down, right? So you notice all the numbers we used were exactly the same. That's why it's so important. I said to, when you write your x0 through x6, now your f of x0 through f of x6 cannot have any errors, or you'd be plugging the wrong numbers in your calculator, basically. So let me know when you have a numerical answer. I'm hoping we all get the same thing. So when I'm doing this calculation, this is actually, I'm doing a decimal here.
Okay, I got it now. I did times 1/2 times 1/2, not 1/3. It's 0.243.
All right, so I'm going to give you a little bit more. 3, 4. If I go 5 places, I'm doing that so we can see where they differ. Now, would you say those answers are very, very close? Well, duh, yeah, they don't differ till the third place. Now let's go back to our original. I keep erasing things. In a classroom, I would not have erased anything. All right, so log 7/8 is approximately 0.24324. So what do you notice? You notice that the Simpsons rule calculation didn't differ until the 4th decimal place. The trapezoid rule calculation differed in the 3rd. Now, in both cases, they're ridiculously close, but this one is just a little bit closer, okay? Now, I find the majority of the problems that I do, Simpsons rule is usually a little bit closer. But again, if you have a problem that's not changing much, the Simpsons rule and the trapezoid rule calculations are almost always going to be really, really close. You're never going to be exactly the same. You can't. You have different coefficients. But the nice thing is that both of them yielded answers. Think about it. We did n = 6, and the Simpsons rule was accurate to 3 places. What if we did it, n = 60? Now, I wouldn't do that problem by hand. Like I said, I would write a simple do loop and have the computer do it. It'd be a lot easier. But the fact is that you get ridiculous accuracy in a really
It's like 1,000 times.
But the thing is, you get really good accuracy really, really quickly. So, all right, William, you got a boo-boo somewhere. I know these answers are correct because Gil got the same thing. And we know Gil is the master of calculations. No, actually, because he agreed with me. That's how I know. Oh, is that what you did? No, I don't think that's the error. I don't think that's the error. But it's just, this is why I want to do this as a group, why I want all the calculations as a group, because if we all do the calculations together and we all get the same thing, then we rejoice. If somebody doesn't get the same thing, you know what you're supposed to get, do it again, and hopefully you get it. Though again, the way I do these problems, I don't do this. I do the guts. Then I do this. It's just so much easier to do it like that. Okay. So I calculate everything on the inside, then I multiply it by 1/3 and 1/2. Technically, I calculated everything on the inside, then I divided it by 6. And then I got my answer. That's just so much easier and so much faster. Now, most of the time when you're doing the trap and Simpson's rules, your original integral might be worse. It might, it might be a cosine, it might be an e, it might be a square root. In which case, again, you report the values. So let's say that was a square root right here. Let's say nothing else changed, but I put a square root right here. Well, then all of these would be square roots. But I'd still say the square root of 1/15 is exactly what I would write down. I'm not calculating 1/15 and then writing down the calculation, because the moment I round off that, then when I re-enter my numbers, they're slightly different. There's no way I'm getting this much precision if I've rounded off prematurely. Now, when you're reporting the answers, most people will just report 2 or 3 decimals. That's really not critical. If you did everything right, okay? Now, as a general rule, you're not going to have this. On the quiz, I did give you the exact answer for the simple reason that when you got to the end of the problem, you could compare your answer to the exact answer, just to see, okay, if I'm really close, then I think that's a good thing. There's no way you can reverse engineer it. If you do it wrong, you can't fudge it and make it work. But generally speaking, if I told you what the answer is, you did the whole problem correctly, and then you said, oh, my decimal's really close. I told you what the answer was, you did the whole problem, you said my decimal's close. That proves to you that you succeeded. That proves to you that you did everything correctly. This is a really, really simple application. There was no calculus involved, but it is a way. I call it the quick and dirty. It's a way of getting an answer to a complicated question with minimal effort. I didn't know how to integrate that. I used trapezoids or parabolas, and I got a reasonable estimation. That's it. And the best part about it is the number that you use. We used n = 6 is generally always going to be small. In most textbooks, the only numbers I ever see are 4, 6, and 8. And there's no limit. There's no derivatives. There's no calculus. There's no limits. So this one is kind of nice. Now, at this point, until we're done, everything is an application of geometry in the sense we're going to now do things like calculating, not estimating, calculating areas, calculating volumes, calculating surface areas, calculating arc lengths. That's what we're doing the whole rest of the way. Volume is probably the most of we do. So if you're looking at the syllabus, you'll see, okay, area, volume by rotations. And what I mean by volumes is we're going to take an area and then rotate it about the axis to create a 3-dimensional shape. It's cool stuff like that. And that's basically the rest of the way. I believe, let me grab my schedule for a second. So right now, where we be, okay, we just did Simpsons and Trapezoid Rule. We have 1 week of new instruction. So next week, which is week 13, those 2 lectures are the last material that will go on the 3rd exam. So we are 6 lectures in of the 8 lectures that we'll have for exam 3. And most of you right now are at that place where you can look on Canvas. And I want to remind people, because I get asked this all the time. When you go to Canvas and you take your cursor and you hover it over your total, it will tell you exactly how many points out of how many possible. Well, again, you can start doing the simple calculations with the last remaining quizzes and exam. Can I reach my goal A, B, or C before the final by just looking at all points? If I can, great, here's what I need. Now, if I can't reach the goal, then you can go through and say, okay, now, if I take my top 20 quizzes, my top 2 exams, and so on. Well, you only turned in quiz 20 today, and the top 20 quizzes count. So it's probably not a great idea to start going through and dropping all your low quiz scores, because then you're assuming all your remaining scores would be higher. But as we go each quiz, right, you can say, okay, after quiz 21, I can now technically drop my lowest quiz, and so on. If you're trying to avoid the final, which everyone should be, then you don't drop any scores. Everything counts. So I want to remind people that all scores count, which is why that Canvas total is so critical, that you understand we have, after today, 6 more quizzes and 1 more exam. So that's 780 points. But because there's a bonus question on the exam, you can technically get more points. And because I throw a couple more bonus questions in on the remaining quizzes, technically, even though it says there's 780 points possible, that may be more like 830 or 840, with the extra bonus questions. So there's a little bit of play there. Okay, so it's a good place to stop.